Am I audible? Yes, we'll start now. Okay, right. So the problem what we are now talking is about this regression problem. Regression problem using parametric approach. That is what we are discussing now. Parametric approach, right? So put that the parametric approach involved what the model like this: W transpose x plus epsilon. Epsilon is basically the random variable, right? Is the, what you actually observe, which is basically the noisy observation, right? So as this epsilon is random, your t is actually the noisy observation, right? So that is what we are talking about. And this is what is inherent relationship between x and y. This is what this model, right? So you can say that the regression of x can be written as W transpose phi of x, right? This is the way how we relate x and y. And what is not known to us is actually this W. Know this W, you are through. In fact, this basic function, we are assuming that it is well known to us. I mean, that parameters, whatever is available in this basis function. So, say for example, if I'm using m basis function, right? So all these basis functions are known to us, right? The parameters also known to us. Suppose that if I'm having m basis function, we have m tuning parameters available with that if there is a Gaussian base, right? In practice, we use this phi naught of x as 1, right? So that is one thing, right? So the other basis function, we use that as a polynomial basis function, Gaussian on, right? And sigmoidal is also there, right? So that are, those things are recollecting all those things, right? So what is not known to us is actually is W. This is what actually you are estimate. If I know this, the you are true, right? So that is the thing, right? So right, so we are going for uh, you are going to get that value of this based on this training data. So you have the data set like x2 and so on up to this xn, and you have this corresponding noisy observation that is given to you. And in this case, what you are assuming that it is a Gaussian. This one is a Gaussian with mean 0 and variance is 1 by beta, right? So if that is the case, we know that your maximum likelihood estimation ends up with least square solution, least square, right, estimation that can be solved just by solving this matrix. Those things we discussed, right? So we can actually get this W, right, all the way from W naught to 1 all the way up to what Wm minus 1. These weights actually we can estimate just solving this matrix, right? In fact, by using this projection theorem, we identify W can be estimated like phi transpose phi, the whole inverse phi transpose t, right? This is fine. But where is the catchy now? I mean, where is regularization technique, right? The importance of the regularization technique, where it comes, right? So that is the thing what we are going to discuss, right? So now in this case, whatever this W you estimate, right, it is going to be data dependent. If I use one particular data, you get one W vector, right? It works out very well for a particular training data, right? So you see that these are all the training data, x1, x2, and so on up to this xn, right? So your estimation of this w vector depends upon the training set, right? So depends upon the training data, you get different solutions. So in that case, so that will end up with what is called over, right? It means that it works out very well for the training, but when it comes to the testing data, it may not, right? So it is not going to have what more generalized, right? But huge data, there is no problem. Suppose that if I'm having a very huge data, right? So n is something like a lakh data, right? 1 lakh, 2 lakh, like that, big data, right? But you see that when you are handling such big data, right? So this matrix and all is going to be really big, computing this inverse and all is going to be that really, difficult to do. So we need to restrict ourselves to some number in thousands, right? So in that case, right, so it is going to be the data dependent, right? So there comes you what is called the regularization, right? So what we are doing in regularization is a slight modification in that objective function to introduce some, right, disturbance, we can say, right? So some variation in this w not fitting perfectly for this, satisfying this equation. We introduce some range for this w naught, w1, right? Some disturbance in that, so we can say that, it is not perfectly fitting this training. That way we are going to do. So the objective function in this case is actually having two terms in it. So in the earlier case, whatever the solution we got, that is the solution for this objective function. It tries to minimize this only, right? So this is what we call it as this least square setup. This is the least square setup. If I'm having only this objective function, the solution for this w vector is going to be our phi transpose phi, the whole inverse phi transpose t. So this is very straightforward. We are getting that. But now we are going to introduce that second term in this, such that this w n square means you are having this w vector, right? W vector is going to have m element in it, right? So you have this w naught, w1, and so on up to this w subscript m minus 1, right? So it is like you are going to square all those values, right? So it is like w naught square plus w1 square and so on. As I'm considering only this real number, right? There is not a complex number. I'm not taking any magnitude here. You can simply square just like that. So this is giving you the magnitude square of the vector w, right? So it is indirectly we are talking about this magnitude of this vector w, right? So that one is also part here in this objective function. In this lambda is called the Lagrangian constant, or in this case we treat them as a regularization constant, right? We are going to discuss about this optimization techniques also in this course. You can understand this lambda is the Lagrange multiplier, right? The same expression, this lambda plays the role as a Lagrange multiplier with inequality constraint. This is the constraint what we are doing. So I put it a statement like this: if I have an objective function, right, which you are trying to minimize, inequality constraint like this, then it ends up with what is called this Lagrange equation with Lagrange multiplier. This lambda comes into play, right? So those things I am going to discuss in the coming class. As far as this class is considered, you need not worry about all those things. Right now, you can think that this lambda is just a regularization constant, right? You can view this as a regularization constant. We are imposing some condition for this w, right? So in original case, in this case, there is no restriction over w, the elements of w, right? You can have any range of values for this w, but now I am imposing some condition for this w. I wanted this magnitude square, right? That also to get it minimum, right? And I don't want that value to be 0 also. If all the values are 0, then it is not a, in that case that will get minimized, but I don't want that, right? So it is like I just wanted to minimize, right? So that should be, in other words, I can say that that should be less than or equal to some value, right? Eta, right? So I'm using this, right? Inequality constraint here. I am purposefully using this constraint to view this problem as, right, the optimization problem. In that case, this lambda is playing the role of Lagrange multiplier. So in that multiplier, right, in that context, this constraint is important. But as far as this today's class is considered, you need not worry about this point, right? You just think about that we have two objective function. This is the regular objective function, and this is the another objective function imposed, right? It is a constraint, right, what you are having now for this W. You may wonder why this constraint. You may have any other constraint, no? So why should I impose the constraint like that magnitude square to be minimized? As I told you, this W is basically modeling, is actually used to model that regression, right? This is like y of x is basically W naught phi naught of ax. Of course, normally phi naught of x is 1. Anyhow, I am writing more general. W1 phi 1 of x, it goes in that way, and then you have this W subscript m minus 1, phi subscript m minus 1 of x. It is like that, right? If the magnitude square is very less, we can say some of the elements are going to be very much less in it, right? So it is going to be approximated as almost 0. So for example, if W1 is something like 0.0001, something like that, right? So you can remove this term in that model. So every time I need not actually use this term for computing this y of x, right? So that type of advantage is there if I reduce this magnitude of this W, right? So you can have, see, this m, normally this m, right? So you can start with something like, say for example 500, right? 501 or 500, right? So you can have this, okay, you can say that m is 500, right? Something like this, right? But effectively, if many of the elements, right, if it is ending up with almost 0, then we can say that the elements, right, in the actual model could be something like 20 or 30, right? So it is around that, if most of the values are actually becoming 0. But we start with m equal to 500, but it ends up with 20 or 30, we are fine, right? So that way the regression model is having only few terms, like 20 terms or 30 terms, instead of going for 500 terms, right? So this is one way to impose the constraint, right? So it is not the only way. We can actually have any other constraint for it, right? No, I'm not saying like that. I'm not saying like that. I'm saying that few of the elements, right? Few elements of this W are going to be that very less. That is what I'm telling. Not all the elements. You have to understand the point whatever I'm telling. What I'm trying to say here is we are trying to minimize only this magnitude square. The squared value we are trying to minimize, right? In that case, not all the elements are going to be around 0. I'm not like that, right? So what I'm telling here is the example, right? So we few elements are going to be almost 0, and most of the elements are going to be what is going to be having some significant value. I'm just telling the example W1, right? It could be something else also, W3 or W4 or W5, something like that. We don't know. Actual, after solving only we come to know about it, right? After solving we can neglect. That is what I'm telling, not the really W1 in this case. I'm just saying the example. If W1 is 0.0001, if, right, then I can neglect this term. That is what I'm telling, right? So the actual number of terms, right, if I'm having 500, and if most of the values are is almost 0, then it is enough to have only 20 to 30 terms in this expression to have a model for this y of x. I'm just saying why you are imposing this condition here, constraint. The main thing is we don't want to have overfitting. That is the main thing. Main thing is we don't want to have overfitting. That is the main reason why we are imposing that constraint. While imposing the constraint, there should be some other advantage, right? So that constraint is this. This is what that constraint what we are having. You can have other constraints also. Like, see, for example, this is the regularization, right? So what is this basically? I'll just explain you that. So this is the objective objective of finding out these w's, unknown, having only two elements, right? So this is having only two elements, w1 and w2, right? So having two elements in this, right? Right. So these circles are the contours. These are all the contours. Contours indicate that, right? So over that one particular circle, right, you are having that same functional value. So this circle, right, so you are going to have the same functional value, and this circle is again having the same functional value, and this circle is having the same functional value, right? It is like that. And what you see here, this is the constraint. This red one is actually the constraint here, right? Now, what you are going to do is, if I don't have this constraint, right? If I don't have this red, right? So this red marking, if it is not there, if I want to know what is it, is W1 and W2, that minimizes this functional value, right? If that is the case, then this is the solution, which is actually having some value in here, right? So this is the solution without constraint. This is the solution without constraint in this, right? I don't have this constraint here, right? So let us say this red is not available. So in that case, only blue circles are available. I am trying to minimize that. This is actually depicting that first term in the above example, right? In this example, the first term, right? This is what I'm talking about, that. And solution is this, right? So it is this, right? So when it comes to the constraint, with constraint, right? I would like to minimize this part also. Minimizing this with this constraint, this should be less than some value. It should be within that range. So if that is the case, the solution now ends up with W star rather than this, right? So this is another constraint what you see here, right? So constraint need not be always the squared thing, right? So you can have something like this also. This is the constraint now. Without constraint, this is a solution. Now with constraint, this is the solution what you are getting for this W. What you are getting here in this case, what is that value of this W1? This is W1 here. This is W2 here. So in that case, what is the value of W in this second case? W1 value is going to be 0, and you have some arbitrary value for W2. So let us say that this is W2 here. So in that case, what is happening here is this W1 value is actually becoming exactly 0, which we call it a sparse, right? So we are able to get this regression model with having what, few elements in it, right? So we are making this W0 as 0. Suppose that if I have the model like W0, okay, having two elements, okay, W1 phi 1 of x, right? And W2 phi 2 of x. I mean, I'm just saying because I'm having only two elements in it. So I'm writing that model like this. And your W1 is 0 in this case. So what is happening? This first term is actually becoming 0. The regression model now it is becoming very simple, having only one term, which is W2 into what? Phi 2 of x. That is what I'm telling. But this is not, this is just for illustration, having only two elements in this W. But imagine that original W, right? Originally we are talking about a very big vector. It is not having only two elements. This is just to make you understand, right? So it goes like this, it is about, I'm talking about in 500 values in it, right? So 500 elements. So out of these 500 elements, if only that 20 or 30 are having non-zero, you are happy. You are making that regression model so simple, right? So that is the reason why we are going for that. And most important is overfitting. That you should not forget. This is another way to understand how the regularization works, right? But you have to understand mainly that, right? Okay, so the constraint is basically your, I mean, you can view that objective function, right? So I explain. I thought of explain this objective optimization problem in a separate class, but as you raise this, I just give you one idea regarding that, not more detail, because today's agenda is different, right? I just Okay, you are is asking this is sparse, right? So this is sparse. I told that sparse is coming because the first element is 0 here. We have two elements in it, W1 and W2. The first element is actually becoming 0 in this, right? So sparse means most of the element of this W values, right? The vector W, if it is 0, we say that it is a sparse. Okay, coming to this, the objective function and constraint, what is that? Okay, that I will come to that one. So that is exactly what we are going to discuss. That is what the exact topic. So please listen fully, and then if you have questions at the end, it is better to ask at the end. Otherwise, you will not, you can't learn, right? So if you keep on asking questions, so you can't really learn it, right? First you learn all those things, and still if you have any questions, I will give you the time for you to ask questions at the end, right? So that is the better way to do this, right? So okay, so as I told you, what you have to understand is in case of the regular method, right, least square method, we are trying to minimize this the first term. Right now we are imposing that second term also in this with the term controlled by what is called this lambda. In this context, as far as this today's class is considered, we call this lambda as what is called this regularization constant. Now I am going to answer the question for this Anand, right, and for everyone. But as Anand mentioned that how that is preventing this overfitting, right? That is what exactly the importance of this regularization. So you can see that experiment, right? So in this case, the experiment is you are planning to um, fit the sine wave basically, because the training data is actually captured from the sine wave. It is actually captured from the sine wave randomly, and you are going to have 100 data set. It means that you have a data set 1 d1, and you have this data set 2, and so on. You have about 100 data set. What is a data set mean? The data set is you are going to sample this x. Let us say x is in radians, and then you have this sine of x, right? And you are going to randomly pick your x and the corresponding functional value, this value and then sine of x. So you are going to capture randomly that points. How many points you are going to capture? You are going to capture this 25 points randomly, right, for one period, right? So you are going to capture like 25 points in each data set. Is going to have 25 points here. This is again 25 points like this, and then 100 data set you are going to use. So you are getting this 100 data set now, right? And whatever you have captured, that is going to have the noise. That is important because it is not a perfect sine wave you are going to have. I mean, captured from the sine wave. Instead, the sine wave after adding noise, right? So it is not a perfect sine wave. Instead, you are going to have some noisy sine wave. That is the problem, right? So you need to have that t only you are going to observe, right? So in this case, the model is like this, so t is equal to, right, you are having this sine of x, right? So it's a function plus the noise, and of course this noise is having this mean 0 and variance, some variance we are having here. So you are actually capturing the data from the noisy, right, observation. That is t here. You are getting, actually this is basically sine x is the green one, and this yellow one is this sine x plus epsilon, that random noise, right? So what you see here is the sine x plus this random noise. This is the random variable, and this is what your t, that yellow color what is available here is the noisy observation. And you are actually collecting about this 25 points, right, randomly here, right? Your x value and the corresponding t values are collected here. So 25 values are there for the individual data set. So this is like that. Now what you are going to do is you are going to do this parametric approach, the right. So you know that model y of x is what, w naught phi naught of x, right? So phi naught of x, and you have here w1 phi 1 of x like this, and so on. You are going to have W m minus 1 phi m minus 1 of x. This is the model, and in this case the m is chosen as 25. M is chosen as 25. This experiment involves choosing this m value as 25 here, right? And of course this phi naught of x is going to be 1, right? So this one we choose it as 1. We'll discuss the reason also later on, right? So this one is phi 1 of x and so on up to this phi m minus 1, and these are all the Gaussian basis. That is what is chosen to fit it, right? Gaussian basis, right? So you know how to solve for W. You are going to use the regularization method, right? So you know this is solution, right? So you are going to use this function to get a solution for this W. W is basically phi transpose phi plus lambda I. The regularization is coming to picture. Transpose T, right? When this lambda is 0, is not having any regularization, you get it as the original thing. But right, so now here we are going to have this constant. We are actually estimating this W, right? So now what you see here is there are many sine waves here. There are many sine waves here. You can see that it is not exactly sine wave. I'm sorry, it is not sine wave. The many fittings are here to fit this sine wave, right? So every wave, right? What is, you can see, imagine that there is something line like this, and then one more line like this, then one more line like this, and so on. So there are many fit for every data set. You can actually imagine, right? You can have more number of fit here. So we have actually 100 data set, right? Right. This are all the individual. See, actually somebody is asking that question, Vikash, what is the difference between data set and data point? See, what we are doing here is the points, whatever is collected, this is the experiment, right? So whatever the points we are collected from the sine wave, x and sine of x plus epsilon, I hope, right? So I write it here. You have x and then x1, for example, and then you have the observation t1 and x2, and you have this t2 and so on up to x25, and then we have this t25 here, and then still you are keep on continuing x26, and then you have t26, right? It goes all the way up to what, x50 here, and then you have this t50, right? It goes like this, you know. You are keep on collecting this, right? Keep on collecting this, right? Like, you know, up to x 2500, and you have this t 2500. This is the data set what actually you are having, but now you are going to group once in 25. This is the first 25, this is the second 25, right? The number of data points in each group, this is the data point, right? So this is what you are actually having, this data collection is 25 in each. You understood that point, right? So for every data set you are going to get what, 25 each. That is what I'm telling. So that is the problem, right? So the regularization problem is that one only, right? It is a data dependent, right? So if I use this data set, you get the regression problem fitted like this, right? If I use this data set, I get a different fit. If I use this data set, I get entirely a different set. You understood that, you know? So we have more number of fittings available, right? In fact, 100 possibilities are there, because we are having what, 100 data set, but just for showing, it is not shown all the 100, it is shown only few, right? So for every data set, it will end up with what, different fitting. That is what I am trying to say, right? So you are it is not ending up with the same. It is like this you are getting, right? Now what I'm doing now is, this is an experiment with choosing that lambda value arbitrarily, like 2.6. Non lambda is chosen as 2.6. So that is a value we have chosen in this, right? if it is for this value, right, for the various data set, all the possible curves what you are getting. Now what I'm going to do is I'm going to take that averaging over the values across, right? So see, it is like, so you are having the different curves available, right, across one particular x. I'm trying to find out what is that average of this value and this value and this value, right? Average of these three values. If I do so, what I am getting is in the right hand side, this red. Red is the one what you see it in the average of these three, right? But your green is the original sine wave. We expected this green from this regression model because we know we captured the data only from the sine wave. So you are expecting that regression to be the sine, but you are getting something like this, and even that average is actually having what, deviating like this, right? Okay, now we'll go for the next choice of lambda. You see that here I have chosen this lambda value. Ln lambda is minus 0.31. In that case, you see that what are the possible curves you are getting? These are all the possible curves. They are actually getting deviated from this. When you see this one, they are closer to each other, right? So all the possible curves here, they are closer to each other, right? So it is, they are, closer, right? But here we have a good deviation. The values are having good deviation. For example, one particular x, if you consider, right? So in one of the data set, it is giving this value, the another data set, it is giving this value, another data set, it is giving this value, and so on. If I use various data set, actually we are getting, it is actually predicting a different points in the regression model for a particular x. It is like that. But is very important. But when I take this average, you see that this is so close to the original, and that is the importance of this regularization. If I take this averaging over all the possible fit here, what actually you are getting here is this red, whatever that regression model, averaging over that regression model, various regression model, that is actually ending with so close to that original fit, even though the individual fit is not proper. The individually the fits are not good, right? So in one case, you are getting that fit like, something like this. In another case, you are getting fit something like this, right? So you are having different fit, for different data set, right? But when I take that averaging over all the possible fit, right, between 0 to 1, you are interestingly getting that, that is so close to this green in this case. So that is the importance of this regularization. You can see, for example, still, so here your lambda value is something else. Now it is minus 2.4. In the previous case, it is minus 0.31, and here it is 2.6, right? It is like that. Now still the variation is larger in this. The variation is larger for a typical x. If we consider x1, for example, in this case, the variation is larger in this case. You see that there is a big variation here. The different data set is giving you the different values in this, like this. But when you take this averaging over all possible curve, it is almost matching with what actually we expected. This is a perfect, almost perfect, right? So this is almost perfect, right? So now, because of this, this regularization, we are getting different fit, but still, when I take this averaging, you are actually getting this, right? It's going to have what, this almost perfect fit in this, right? So between the lambda and the fit of the average, yes, that's what the next slide is, right? So, okay, right, okay. So yeah, that's one I just wanted to tell that point, right? So before that, these are all the different regularization, right? I think what I shown in that slide is this and this, right? I didn't actually shown this q equal to 0.5 and then q equal to 4. The q is basically the power of this w. So in this case, this power this power. You can make it as more general, right? So if this q is 2, you get the contour like this, the constraint contour, right? So this q equal to 1, it is like this, q equal to 0.5 is like this, q equal to 4 is like this. I have shown this 1 and 2. So this is just to make you understand that there are still other possibilities you can have, right? But what is more important is, as somebody is saying about this importance of this lambda value increasing or decreasing, how this average value is changing, right? So that is the thing. As you see here, the error involved in that thing, right, in regression, right, the error involved in regression problem is actually, we can split as that bias squared error and then the variance. Of course, the third one is also there, which we call it as this noise. We just call it as that noise, right? So we cannot actually, this is basically the error involved in regression. The error involved in regression can be splitted as, right, you have this bias square and plus variance plus the noise, right? So I will explain you, right, what lambda to be chosen, right? So to understand about this bias square and variance, first of all, how that is computed, that you can see that the bias square and then variance, right? This is that bias square and this is that variance here, right? So let me put for understanding purpose, right? So you consider only three data set, having three data sets. So this is the one curve using the data set 1, right? So you are having this data set 1 in this, and you have this data set 2, and you have this data set 3, right? Three data sets are there. Using this data set 1, right? So let us say that it is this one, so we are getting this, and using this data set, getting another curve, and using this data set you are getting this another curve, right? So this is a three, right, plot regression model we are able to get, right, because it is data dependent. So this is what you are having now. So now what is that bias square? Bias square is, you have to take this averaging over this curve, right? Averaging over every point, say for example point here is, say for example xn, and you are going to take this average of these three, right? So that one we are calling it as y bar of xn. So that is the term here, y bar of xn, right? But you know that the what is expected at xn, right? So say for example, this particular example, it is a sine wave, right? So at that particular xn, what is that you are expecting? You are actually expecting this value, right? So that is my h of xn, right? So now this average y bar of xn, right, this y bar of xn minus this value, right, this is what we call it as h of xn. This is h of xn, and you are finding out this error, y bar of xn minus this h of xn, right, the whole square. This error you are actually finding out. Remember that what I'm doing is very important. You are taking this averaging over all the values here, that is y bar of xn, right? The original value, it is going to be your h of xn, right? And you are trying to find out the difference, y bar of xn minus h of xn, the whole square, right? So that way you are trying to do, and you are actually doing this one for all possible values of n. In fact, even though whatever I am drawing here, everything is continuous, right? So this is the continuous plot, right? But actually speaking, in this job we are going to do it in a discrete form, right? So it is going to have something like, anyhow, when the moment you use computer, it is going to be a discrete, right? So you have some finite number of points in this, that is xn here, right? If I do this for all the points, n is equal to 1 to n, right, and then taking the error y bar of xn, and then this is h of xn, the original one, the whole square, and do the summation and take the average, and that value is what we call it as this bias square. Fine, bias square is fine, right? Now what is that variance? Bias square, what is actually it is giving you? Bias square is giving the information how far the averaging over the regression plots, whatever we got with various data set, is actually closer to the original, right? So this is the averaging over all possible with the regression model. How far this is closer with the original, this h of xn, right? So that actually it is, if I do this summation square and taking that average, and that is actually giving you that bias square, right? But now you have another term called this variance, right? So what is that variance? Variance is how far that individual curve is actually deviated from this mean average. So to understand that, let me once again plot this here. You have this three plot in this. Let me have that red plot for this data set 1, and then you have this black here, data set 2, and then you have this green, right? So this is going to be data set 3, and you have averaging over these 3, right? So somewhere, right, let me put it as in yellow color somewhere. This is that average, right? So you have that 3 regression model, green, black, and red, and then yellow is that averaging over that. This yellow is what we call it as this y bar. This is y bar here, right? How far it is getting deviated, how close, right? Because of this data, right, it should not end up with different plots, right? So the 3 different plots, whatever we are getting, if they are closer to each other, we say that it is having less variance in it. It is having less variance in it, right? So for instance, if I consider here, there's one particular x value, xn here, right? So what we are going to do is we are actually finding out this variance. Variance, how will you find out, right? So you have variance with this yellow point. This is the point. How far these 3 values, right? This green point, red point, and black point is deviated from this yellow point, right? So we have to find out this variance of these points, right? With reference to what? The average, right? So that is what exactly we are doing here. Y bar of xn is that average. This L is the data set number. So here it is made as more general. There are L data set available. In this case, it is only 3. In this case, this L value is 3. And the number of data points is actually how many data you are collecting here, right? In this axis, right? So as I told you, it starts with your x1, x2, and so on. It goes all the way up to what? Xn. So the number of data points. So that is n here, right? But in this example, I have chosen this L equal to 3, right? So what actually you are doing here is you are actually finding out the variance, right? So that L is the Lth data set, how far it is getting deviated from that average, right? The mean, right? So if I find out this error, right, we can understand that how far the different curves obtained using these 3, different data sets are closer to each other, right? So it means that if the lambda value is almost 0, right, what does it mean? It is actually, right, it is like overfitting, right? It is like that, right? It means that your curves, whatever you are going to get from this d1, d2, d3, everything, right? So it all depends upon the regularization constant lambda, right? How far this variance and the bias squared is actually going to change, right? So you can see this graph now to understand it better, right? So now when lambda is 0, what does it mean? It means that you are going to have, right? Right? So you are going to have that value of, right? Lambda equal to 0 means there is no regularization in this expression. If there is no regularization, it involves only this first term. You can see that when that lambda is increasing this way, you have this, how this bias square is changing. You can see that the bias square is actually increasing. As lambda increases, your bias square is getting increased. But when it comes to this variance, the red color, right, it is actually decreasing. The bias square is increasing, but the variance is decreasing, right? So as this lambda gets increased, see, so this is the largest lambda, right? So you can see that, right, this red is actually getting deviated from where? The original value, right? Here, even though they are closer to each other, it will less. Variance is less in this, but the bias square, right? So how far it is getting deviated from the original, that is larger in this. But when it goes to this lambda value gradually decreasing, you see that the variance is actually increasing, right? You have variance here, but your bias square is keep on decrease because it is closer to that original value here, right? So when it goes to the next here, again, in this case, still lesser value, right? Your variance still it is going to be the larger in this case, but your bias square is almost zero. It means that it is deviating from original value, right? It is very less, right? So the relationship is what actually we are discussing. The mathematics part we are going to discuss in the next class, right? So we will stop here. Before that, I just wanted to read the last question posted. um, our observations inaccurate. Shift the curve to accommodate slightly random values. It is limited to this data, otherwise it will give high accurate results for training. Yeah, yes, yes. So you want to inform with others, right? Okay, okay, fine, right? So I think you got this point, but once again we are going to discuss this one in the next class, right? So that time I will clarify whatever the doubts you are having, right? So this graph needs to elaborate, right? It is not too simple to explain. I need to do one derivation, right, for the next class, right? So what I want to actually derive is just the outline of the error involved in the regression, what we did now, right, using this data set, right? So it is actually composed of three terms. One is bias square, the another one is variance, and the third term is actually the noise, right? Have control over the noise. We can't do anything with the noise, but there is a trade-off between bias square and variance. If I try to reduce bias square, variance will increase. If I try to reduce variance, bias square will increase. If I want to have a perfect regression, we have to look for a point where this bias square plus variance is minimum, right? So you can see that just the outline of this graph, right? See this color, right? Pink color, right? So what you see that the minimum juncture, right? Somewhere here, the minimum value here or here, right? So left here, so somewhere here. So the minimum value of this buffer and variance occur here, and that is the place where you get the error less the test data. This is very, very interesting result what we are actually getting. What I'm trying to say here is the bias square plus variance, where you are actually getting the error minimum, that is the exact place where you get the test error is also getting minimized. That is the reason we are happy that if it is working for the test data, your work is perfect. That is the way actually we need to conclude, right? So that is the meaning of it. This one, once again, we are going to discuss in the next class. What I am trying to say here is you have to look for the lambda where this bias square plus variance is minimum. It is like that. So this is the place where it is minimum, and this is the place where this you are getting minimum for the test data, right? So we will discuss other things in the next class. We will stop here, right? Okay, is that all right? Good.